All right, we will get started. So, if you haven't yet, be sure to go to dsuprog.club and click View Meeting on the ICPC recap. That way we get you marked for attendance. So, we will recap this past Saturday's competition as shown in the name ICPC Regional Qualifier. So first of all, congratulations to the teams who will advance to the regional round. We took the top 3 finishers. So first place we had Dunder Mifflin Scranton. So we had Ben Iserman, Blake Nedved, Julia Schaefer. NAN 2022, that was us officers. And then Trojans was John Dandy, Elliot Ducharme, and Ryan Morganti. So, and then we do have an alternate, either if we're able to get a 4th team in, we're trying to get that in the process, or if someone gets COVID, we have Shane Donahue, Jake Hintz, and Galen Shoup. So, again, thank you to all who participated. At this time last week, we only thought we had like 3 teams participating. We ended up having 8 teams participate. So that was really, really awesome to see. And every team got at least 2 problems solved. So that was also really awesome to see as well. So everyone did a super awesome job. So for those of you who weren't competing this past Saturday and are wondering, what we're talking about, this past Saturday we had a competition that consisted of teams of 3. It lasted 5 hours, and there were 14 problems. So I linked the problems here on Caddis. So if you didn't get the chance to participate, or if you want to go try and solve some of those problems you weren't able to that day on Saturday, the link is out there, open for the public for everyone to view. So only one person was able to submit at a time, but everyone else was able to work individually on the problems. So some formats you'll see where you can only have one computer open, and the other 2 have to code on paper and then give that paper to the person, and they have to write all the code. Luckily, we didn't have to do that for this round, so it's a little bit easier to kind of get things moving quicker. So there are cons to that, you aren't communicating with your teammates as much if you're kind of narrowing in on your own problem sort of thing. But overall, that's kind of how this competition style was laid out. So the qualifier was used to determine which teams we will be sending to the ICPC Regional. Who is calling me? They aren't. Shut up. So, and so the regional will be placed in Minneapolis sometime in February. There's a date, but I don't remember it because I'm bad at dates. And so we will send those 3 to the regional, and then that will be determined to figure out who goes on to either national or world finals. I don't know if they put a step in between qualifying world finals or not. National. Okay. So national, yeah. Whole rigmarole. So tonight we have a few solutions from this past Saturday that we are going to go through. So for those of you that weren't there on Saturday or didn't get some of the ones solved, you'll get a chance to hear about them. So we'll start out with problem E for those of you who weren't there, and for all the teams that did participate, they did get this one, but just kind of, there's different ways to solve a problem, so we'll give you guys a chance to see how our team did it and see if you did it in a similar way or maybe more complex way. At the end of the day, for these competitions, as long as it works, that's all that matters. But for future reference, if you can make it easier on yourself, that might help. So that's why we'll show E tonight, even though everyone got it solved. So this was my solution. I did this in C++, so we'll make it a little bit bigger. So I did mine in C++. So those of you who did in C, a couple things will look a little bit different, but for the most part, it's all the same. So I have my libraries included. And so I made a couple variables to start. I first took the input string. One second, my apologies. Let me explain what the problem was first. That would probably help. Okay. So basically, there's this whole dealio there's a long story with this one, but for this one it didn't really matter as much to get the input read. Basically what needed to happen was, with your input, you need to have an equal number of bars on either side of the parentheses to have a like centered I or whatever. And so if it was uneven, you had to output fix. If it was even, you had to output correct. So here's some sample inputs, as you can see. And so yeah, strings were at least length 4 and up to 100. So now that I have the problem explained, I can show the solution and have it make sense. So I first started with an input string for us to read in that string that was given to us. And then I made two integers counting the left side of the bars and the right side. And then I made a Boolean for parentheses to let us know when we need to switch over from counting the left bars to the right bars. And so you'll see the C in here. This is C++ for just reading in a line. So the equivalent would be scanf, %s, and input sort of thing in C. And then we have our for loop here. So starting at 0 and then going to the string length is what this is. So you can also, calculate how long your string is, reading that in through C and use that variable. C++ just has a nice way where you can say, give me the length and keep moving. And then within there, I checked what kind of character I read in. So I first checked to see, that it was a bar, and that by parenthesis being false means we have not seen a parenthesis yet, so we're adding to the left counter. So that's what I did here. Otherwise, if I do see a left parenthesis, I change that to true. We have seen a parenthesis. I didn't account for anything for the right parenthesis because that's not as important. We just need to make sure that we set this Boolean to true. I jacked that up somehow. And so then once that's the case, once again, if we see a bar, but this time a parenthesis is true, then we increment that right counter. So once we hit the end of our string, we have hit input length. And so our for loop will break, and then we just need to simply check. Does the left count of the bars equal the right count of the bars? If that's the case, print out correct. If not, print out fix. So if we compile, so G++ is the equivalent of GCC. I use G++ for C++ files. So then if I put 3 on each, we get correct. If I put 2 on one side and then 1, we get fix. If I just do parentheses, it's correct even though it would be input 4, but you get the point. Or if I just did like this and didn't have like a closing, tell me to fix, etc. So pretty straightforward. I know, yeah, some could have gone a different way with kind of doing it, but this is just kind of the brute force way of getting E solved. And so that's kind of sometimes the easiest way is try going brute force first and hoping that it's under time like constraint, and then if it's not, finding a more efficient way. But for this one, it was short enough and small enough and quick enough that just doing straight brute force worked for E. So yeah, that was problem E. So then we also had problem G solved, and Nick worked on that one. So we'll hand it over to him.
Okay, so problem G was the code format grader. And basically this one, the main problem was just in string processing pretty much. The input, what you have is an amount of lines, how many errors you're gonna be given, and then the line numbers for each of the errors. And then what you want to do is format that in such a way that all the continuous runs are grouped together and all the errors are listed, followed by all the correct correct lines without errors. So what I did to solve this, I also used C++, but I'll explain how you might do it in just C. First started with some basic variables, the first two digits that were given, the number of lines and the number of errors. And then I also added a temp variable, which is a surprise tool that will help us later. So you just read in the input, however you may do that in the language you're using. Then we need to take the, here's the browser. Then we need to take all of these errors and just throw them into an array. So that's what I do here. In C++, you can technically do this. It's not recommended, but it's easy. Another way you could do this if you want to be better, but not that much better, is you can just set this to the max number it will ever be, and I messed something up, right?
Oh, I got it.
Oh.
Control-Alt-V. There you go.
Okay. Another way you could do this, I believe 100,000 is the highest the n will ever be if we look at this. And that's inefficient, but it works when you're in a competition. Otherwise, you can use malloc if you know how pointers work and can make sure you're not doing bad things with memory. But once you have that, we just loop through and get the input and throw it into the array. If you have the 1000 sized array, then you might want to leave a marker at the end slot in the array that says that it's the end. Let's see. Okay, so here's the first big C++ thing in these explanations, which is vectors. For the purposes of this meeting, you can basically just treat vectors as arrays, but cooler. You can do array things with them, but easier in certain circumstances because you don't have to define the size. An alternative to this might be defining the size of an array or doing weird stuff with data structures like you might do in CSC 250. But generally, vectors are a very good thing to know about in programming competitions if you're going to be using C or C++. Well, C++, but if you're going to be using C-type languages. So first what we got to do, or here, I'll explain this whole thing in general terms first so that this makes more sense. But if we go back to here, we're finding the clumps of numbers and then grouping those together. So how I decided to do that is start at the first line, check if that's an error or if it's correct, then move on and find what the next one that's the opposite of that is, and then count that clump, then keep on doing that, trading off error correct, until eventually you've got your clumps of errors, you got your clumps of corrects, and then you can just throw them into the output by looping through your array. So these couple lines here just determine if that first line is correct or an error by determining if it's an error, because if error 0 is equal to 1. Then we need to loop through, but we're not looping through like an array. We're just starting at 1 because that's the first line number, and then we're jumping ahead once we've found a clump to the end of that clump. So the structure of this is I equals 1. I is less than or equal to C because we're starting at 1. And then I just left this empty because I'm doing more complicated things in the loop. And then I also kept track of an index in the error array, which is the current error, which is basically just starting at 0, being like the first error when you're on the first loop, and you need to see, okay, what's the next error? The first one will be the error, and then later on you increment that to be like, okay, this is now the next error. But yeah, for each chunk, we use this variable from here to say if it's a correct chunk or an error chunk. The correct chunk, we start by finding the last, we start essentially by finding the next error and then going one back from that, and that's the last non-error, or the last correct one. So if our next error is less than n, which means that if it doesn't go off the end of the errors array, then we'll just say, okay, this next error, we subtract 1 from that, and that's our last correct one. But otherwise, it'll just go to the end because there are no more errors, so we need to set that to C, which is the amount of lines. And then after that, we make the string for it so that we can output it easily later. If our next one is the same as the current one, that means we've only got one, so we don't need to do the hyphen. So we just add that to our strings. Otherwise, we add the first number, a hyphen, and then the next one. And then we reset a couple variables so that they'll be good for the next iteration. Correct is false because we currently are at a correct chunk. Then we're finding an error, so the next one will be an error chunk. And then we move up the loop iterator to be at that next error because we've dealt with all the ones before that. So that's the first half of that loop. The second half is when we're at an error. We need to keep track of the amount of errors that we're finding, and we're just looping through the list of errors until we find one that isn't just the last one plus 1. So for j equals error plus 1, j is less than n, j plus plus. If the errors j is not equal to errors j minus 1 plus 1, then we just break out of the loop, but otherwise we increment the count variable. So if it's just 1 and there aren't any after it that are consecutive, then count will be 0. Otherwise it'll be however many after it there are that are consecutive. So if it is 0, we just push back the single string onto the array. If it's more than that, then we need the hyphen thing, and that's the same as above. And in this case, we need to set the next error in addition to doing the two things above that we also did above for setting up the variables. And in this case, the error is, it's just one after what we were at. Or yeah, it's one after the amount of, wait. Oh yeah, no, we're incrementing the amount of errors that we found so that we can get to that last one that we found. Then we add one more to get to the one past that. Then we just need to print out everything. So just the string. Then we loop through the whole array and print out the elements there. And we just need to be careful about the commas and the ands and stuff. In this case, they didn't use the Oxford comma, so they are dead to me. But that means that for the last two, you don't need the comma. And for the last one, the second to last one, you need an and instead of a comma. And then you do the exact same thing, but with correct and that array there. Any questions? Okay. Next is problem J.
Okay. How do I on full screen again, Aaron? How do I on full screen?
Escape.
Oh, I can just escape.
Or,
Oh, wait, I'm not in the presentation anymore.
the DX.
There we go. Okay. So, Jay's got a lot of text, and it looks really complicated, but it's actually a lot simpler than it looks. So, basically this guy works at like a pancake restaurant or something. No, it's just stack-related products manufacturer. And so he has some calculator called the Stackulator 3000. And it just takes some program, which is just some mixture of the three characters 1, D, and plus, which build up a stack of numbers, as you can see in this picture here. And so your goal is basically to feed it the program to generate a stack, which is the input. So down here on the bottom, this stack is 1, 1, 1. So each of the three symbols that you can put in a program, 1 puts a number 1 on top of the stack. Pretty simple. D duplicates the top thing on the stack. So if there's like a 1 and you put a D, then it'll put another 1 on top. But if there was a 2 and you put a D, it would put a 2 on top. And then the plus takes the two things on top of the stack, removes them, adds them together, puts it back on the top, and then decrements everything else below it by 1, which that actually makes it a little bit harder because you have to worry about it decrementing all of the numbers lower on the stack that you can't change anymore because you can only modify the ones on the top. So the way that I approach this program is I actually took the input and I just reversed it because the things on top matter the most. And the reason why I did that is because if I was to put, let's say the stack was 1, 2, so I had to do the numbers 1, then 2. If I just put a 1 and then put 2 more 1s and added them together, it would decrement the first one and they'd be down to 0. So it would be wrong. So I did it in reverse, where I made the 2 first and then the 1. And then I counted the amount of pluses I used because it lowers the number. And then made the numbers on the bottom bigger. So I guess it's kind of hard to explain how that works, but the main problem that I had with this problem was I went down a rabbit hole trying to figure out the shortest way to make a number. I originally tried doing it in powers of 2, because if you just keep duplicating the number and then adding it, you'll get powers of 2. It'll go 1, 2, 4, 8, 16. So I figured that was the best way to go. But I went down a rabbit hole for like 30 minutes and it didn't work out because they got really long. Because the program has a maximum length, which the input will make you hit if you do it badly. So I decided to just do it by continuously subtracting 1 and then dividing by 2 until I got down to 1. So if the number was even, I divided by 2 and then remember that, and then if that number was even, I divided by 2, or if it was odd, I would subtract 1. It basically is just the shortest way to represent the program, because basically you could just do each number as a separate program, and then at the end you could combine them all together to get the final answer. So I will show that here. So I did this one in Python. First I just read in the input and I reversed it. I could have just iterated backwards, but I didn't want to. So then at the bottom, which is where it actually runs, I just looked at all of the numbers I was supposed to get, and then I generated the number for the program in reverse, and then I counted the amount of pluses before it because that would reduce the number. So I just generate it higher, so when the pluses reduced it, it would be the correct number still. And then a minor optimization was if two numbers were the same, you could just duplicate it. You don't have to make the number again.
Is gen number like a built-in function, or?
No, that is this function up here, which is what I said of how I was able to get it to make the shortest program for a number. So like, if I was at, let's say I wanted to generate the number 5, the shortest program for 5 is 1d plus d plus 1 plus, which just means put a 1 on the stack, then duplicate it, then add them together, then duplicate that, then add them together, and then add a 1, and then add them together. So the way to find this program was to remember, or was to do this short algorithm that I came up with, which is if the number's even, I subtract 1, and that would give me 4, which is this 1 plus here. And then since the number's even, I would divide by 2, which would give me the d plus that I have here. And then since that number's even, I divide by 2 again. And that's this d plus, and then obviously I'm at 1, so I just put a 1. So all that function does is generate that little string. And then once they're all generated, they're in an array, so I just reverse it again because I reversed it at the start and join it back into a string. So if do you have a Python interpreter? I guess we'll see. Haha, you do. Okay. I'll just run on one of the inputs. This one's really simple because it's just 3 ones, but I'll do this one. So there you go, that's the same. I guess it's kind of hard to tell. Just can't really compare them by number. Actually, they're not the same. This one was weird because the answer didn't have to be the same as the test case output. It just had to work, which made it harder to debug. But once you got the fundamental of the algorithm down, it was not a hard problem. It seems like it's a lot harder than it is.
Okay, so problem L was combinatorics, everyone's favorite. Okay. So basically, they gave us a big graph, and then we have to count how many of these sword-shaped subgraphs are inside of it. And basically, that's defined by one. They just have to be connected in the shape, and each vertex has to be distinct. Yeah. And then they passed in the graph as the number of vertices, then the number of edges, then each edge pair as its vertex indices. So then, so first I just read in those two numbers that were the number of vertexes and the number of edges. Then I created a default dictionary with its default being a set. So basically that creates a dictionary And then anytime we access it, it's first going to put an empty set in that entry, and then we can modify that. Then we read in all the edges, just add them to the edge. Basically the way I store the graph is a dictionary between every node and then its neighbors in a set, and just add both directions on the edge. This is the binomial coefficient function. The simple version you can write is not fast enough for it, so I stole it from Wikipedia. Yeah, I stole it in the last competition too. Use the same function. Yeah. Oh yeah, then this is how the algorithm works. So we go back and look at it. So the way I figure out how to solve this was we iterate through every node in the graph to check if it could be our D node, and then if it has less than 4 neighbors, then we'll just throw it out. But if it has 4 or more neighbors, then we'll look for each of its neighbors, could possibly be the B node, and then for every one of those, we do combinatorics to figure out how many of the other 4 nodes could be picked out of them. And that's complicated because I can just draw on this. You have a pen?
It's in the side there. I just took off a little bit.
Got it. Yeah. So if we have some, I guess this one's D, this one's B, A, and then it was C, E, and F. So, ooh, I've never used OneNote ever.
What'd you say?
I've never used OneNote before.
Oh.
This is an interesting experience. But basically, we take all the neighbors of D and put those in our group, which is, I believe I have that. Oh, crap. We'll just ignore that. So that's this, D edges is what that variable stood for. We just get the edges for D, then we count them and put that into DN for later. And we do the same thing with B. And then here we do DC is basically the number of neighbors that are not the other of the B and D, which are the possible selections for A, C, E, F. And then it does that for both of those. And then where it's complicated is that B and D, the neighbors of those can overlap. So we have to check how many overlap too. And then make sure that we're counting the overlaps properly in our combinatorics. So then it's pretty basic. We just have to like, go back. We choose 3 of the neighbors of D as our C, E, and F, and then we choose 1 neighbor of B to be our A. So that's essentially just the neighbors of D choose 3 times the neighbors of B, but we have to discount the overlap there, and then we add a second term accounting for the overlap, which is this one. So basically we just do the nodes that are not overlapping in the first one, and then in the second one we do only the nodes that are overlapping, and then we basically say that D has 1 less neighbor. And that's about it. Yeah. Again. Yeah. Any questions? Okay.
Thank you to everyone for sharing. I'm guessing there are no questions, but we threw that slide in there anyway. So, yeah.
Just in case anyone wanted to see solutions for A, I, or K, I do have those.
Okay.
So I could present those if anyone's interested.
Okay. Sounds good.
The regional will probably be 1 computer only.
What?
The regional will probably be 1 computer only.
Remote computer only?
No,
One computer only. Yes, probably. Probably.
And you
Did you say we were sending the 3 teams to regionals?
Yes, and potentially a 4th, but
Okay.
three for sure right now.
And it'll be on Saturday, February 26th.
Perfect.
don't have access to the internet.
What?
You don't have access to the internet. So, actually, but you can use official
Oh.
documentation, but you can't like Google stuff.
Gotcha. Makes
So if you
sense.
want algorithms, you have to bring them on paper.
Because you can't even have like preloaded files this time because you have to use their own computer, right?
Full of Python one-liners.
For your flash drive.
Don't worry, I've got a packet.
Oh.
I didn't make it. Just got it.
You could make it.
Good to know. Good to know. I'm just happy we're doing it in person. All right, I'll end the recording here. Any last minute questions?
Yeah, so for the regional, do we bring our own laptop?
Don't even bring it.